In this video, I'd like to do some specific examples on how to set up cross sections perpendicular to the x-axis. So I've already drawn a graph here with a parabola that was opening downward, a line, and I found the points of intersection. What I'm interested in is taking this base or bounded region and slicing it perpendicular to the x-axis. So my first order of business is to establish exactly what each of these bases would be. My base would be the parabola minus the line. And since these are going to slice the x-axis, I want everything in terms of x. So I'm going to take my negative x squared plus 6x minus 4. That's the parabola I have here, negative x squared plus 6x minus 4. And I'm going to subtract the line, so it's top minus bottom. So I'm going to subtract x. That means that I can establish a base of negative x squared plus 5x. Almost messed up there. 6x, take away x is plus 5x, minus 4. This, for all intensive purposes, is done. I have a base. Now I'm going to go through and I'm going to set up the various types of slicing that I could be asked for. Now this is not all of them. There's other things that could be asked, but this is a good chunk to get you started. And so I've got my base. I'm going to go to this piece of paper. And I already wrote out what we were looking for. So first I'm looking for the equilateral triangles. Now as I look at my drawing, I can say that the volume will equal the integral. It starts at x equals 1 and it would end at x equals 4. So I'd say from 1 to 4. Now for an equilateral triangle, in the previous video we established this universal formula. We said that the volume would go from A to B of rad 3 over 4 base squared dx. And I showed how that was developed. So all I have to do is recycle that. I say radical 3 over 4 times the base squared. Now I have a value for the base now. That is the negative x squared plus 5x minus 4 that I'm going to square and then say dx. Now the calculus part, you guys can do that. That's simple. But this is the setup. That I had 3/4 the base, whatever that base value turned out to be, squared dx. Now I can either put that in a calculator, or in some instances I may be asked to actually triple distribute, expand that, and then integrate it, but that's really not that challenging to do. For the second question, I'm asking to do a 45-45-90 where the triangles have the hypotenuse on the bounded region. And again, in the previous video, I set this up. We've got a formula that says if we're going to work with 45-45-90 right triangles, we're just going to take 1/4 the base squared. So for this one, I would still have the integral from 1 to 4. Then I say 1/4, and I specifically take that base that I calculated. And most cross-section problems will be done this way. They'll give you a region and then they'll have like part A, B, C, D, or part A, B, C, D, E, or whatever, where they're just going to ask you to go through these different types of cross-sections that you could create. And so on this one, we said that was going to be 1/4 whatever my base was. So this part doesn't change. Squared dx. For part C, it says semicircles. So you start to see this great similarity. When I did the semicircle, we had a formula that was just going to be 1/8 pi the base squared. So I have my 1/8 pi the base, just going to be the same setup over and over again. That's why they have you do the part A, B, C, or A, B, C, D, or whatever, because this part really doesn't change from problem to problem. Now I've got my rectangles. The volume equals the integral from 1 to 4. Now this is a rectangle with height of 3, so that would be 3 times the simple base. It's not going to be a square because this is already a dimension. See, these others, when I'm working through these are part of the formula. This is not a dimension. Here's the 2 dimensions. 2 dimensions. 2 dimensions, which was creating the area, multiplied by the dx, which was your third dimension. On this one, this is a dimension. This is a height of 3. The base is just the simple negative x squared plus 5x minus 4, not squared. It's just boom, boom. 1, 2 dimensions. Dx makes the third dimension. And then I'm going to do another one on this. We're going to do a letter E. I did not write that beforehand. Let's say we had squares. And you see, even me just adding this on here, very simple to do, because now I can say I would have volume equals the integral from 1 to 4. A square is just base times itself, so it would be that negative x squared plus 5x minus 4 squared dx. And all of those were with respect to the x-axis. I was crossing into the x-axis. I'll do another video where we'll go into the y-axis. We'll cut perpendicular to the y-axis. So here's your examples on how to do specific cross sections that are perpendicular to the x-axis. Perpendicular to the x-axis. And you can see all I did was invoke each of those formulas. For equilateral triangles, it was rad 3 over 4 base squared. For 45, 45, 90 with the hypotenuse being bounded or found on the bounded region, that was 1/4 the base squared. Semicircles was 1/8 pi the base squared. Rectangles of height 3 or height 5 or height 7 or whatever that height would just be that number times the base. No square on that, because that is a dimension. 1, 2, 3 dimensions. And then we did our squares. Squares was just going to be that base squared. There's 2 dimensions. Dx was your third. So there's your cross sections perpendicular to the x-axis.